What happens if you multiply a set of prime numbers and then add one, a prime or a composite number? You get these numbers. This is a new prime. This is a composite. This composite is divisible by 59 and 509, both prime numbers. With just that, we have everything we need to understand Euclid's legendary proof that there are infinitely many prime numbers. Let's math travel into the beautiful logic behind Euclid's proof. These two numbers were created by multiplying some prime numbers and adding one. Naturally, the result is larger than any of the primes we multiplied, because we multiplied the primes greater than 1 and added 1. In our example, one of the results is a new prime, the other is composite, but it's divisible by primes we didn't use originally. So no matter what, this process always shows us one thing. There are always other primes out there beyond the ones we began with. Even if you think you've listed every prime that exists, I can still show you a new one. Just multiply all the primes on your list and add one. That new number will either be a prime not on your list or a composite that's divisible by primes not on your list. That's the core insight behind Euclid's proof. How exactly did Euclid prove? He used a classic technique called proof by contradiction. He wanted to prove that there are infinitely many primes, but instead of proving it directly, he assumed the opposite, that the number of primes is finite. Let's say we write down a list of all the primes in existence, P1, P2, P3, up to Pn. Now, multiply all of them and add one. Call this P. This new number P is not divisible by any of the primes on the list. Why? When you divide P by P1, the quotient is this, and the remainder is 1. When you divide P by P2, the quotient is this, and the remainder is also 1. No matter which prime you divide P by, the remainder is always 1. P is not divisible by any of the primes on the list because of this plus 1. So P must either be a new prime or a composite divisible by other primes not on the list. Either way, we've just found a new prime not on the original list, which contradicts our assumption that the number of primes is finite. So the assumption must be wrong. There can't be only finitely many primes. Therefore, there are infinitely many prime numbers. That's how Euclid proved it. Simple, elegant, timeless. Did you enjoy math traveling? Please subscribe for the next trip.